To be serious, see, you've pulled out this same old canard. No offense, I apologize to anybody that thinks that I'm mocking or condescending to them when I'm instructing and taking an educational attitude about physics. I'm not taking this about my own ideas. These are what the tradition of physics told me as well as I could understand them, okay? Check yourself, but I'm not trying to push my ideas this way. You can see how I push my ideas skeptically every day. And I don't say you can't deny physics. I just don't like that you're going to say, no, I'm drawing it from physics because physicists agree with me, when they don't. I don't like that. Okay. You pulled out this old canard of quantum physics doesn't account at our level. What about glass? What about all the devices we can build that have an effect at our level? Think about it this way. This piece of paper, it is made of magnets, but it's not magnets. It doesn't have a magnetic field that I can notice. It doesn't stick to metal. It's not a magnet. You're telling me it's made of magnets? Oh, okay, I believe you, but magnetism only affects the microscopic scale, obviously, right? No, magnetism affects this whole thing. Right, magnetism still affects us. Just because the law of averages comes into play and the random arrangement of the magnets in here mean that they cancel out more than they add up together, that doesn't mean magnetism doesn't have an effect. Somebody said the same thing about the uncertainty principle. Nobody's ever proved the uncertainty principle holds at the macroscopic scale. Are you what? Yes, they have. The uncertainty principle absolutely holds at the macroscopic scale. The only issue is that you can know the momentum and the velocity pretty well because of the wavelength of the object. Hello? It, of course, holds at this scale. When you break something down and show that these laws hold in every little part of it, it holds when you add it up together, too. Just because the law of averages make it cancel out doesn't make it go away. Just like it doesn't make the fact that you can rely on a pattern. You can determine a pattern that something's going to hover around when you have a statistical sample. That doesn't make things determined. You know, and the fact that they usually cancel out doesn't mean that they're literally zero suddenly at that scale. Right? And it's just like magnetism. You look around, how many natural magnets you run into? Not many. It only affects the microscopic scale normally. But we can make magnets real easily because they really are always magnets, the atoms. Really. And this also magnetic. It's just that mostly it has a very, very imperceptible magnetic field because it's been canceled out. It doesn't not apply. How conceptually can you think that it not applies? What really is going on is that if I use as an approximation this thing not having any magnetic field, I won't go too far wrong. It's an okay approximation. Because of the law of averages and the magnetic fields canceling out, when you have terms naturally canceling out, if you just pretend they aren't there at all and ignore the little tiny bits, it makes the equations a lot easier to solve, and so the approximation holds. Okay, it's like with Newtonian Newtonian physics versus general relativity. People like to say, oh, but in non-relativistic speeds. All speeds are relativistic. General relativity doesn't go like, well, at 50,000 miles an hour, this no longer works. No, it works all the way down to zero velocity. It works. General relativity always applies. The only issue is that the relativistic component is so small that why calculate it? It's known to be small unless you have this so-called relativistic velocity. These are rules of thumb about when it's okay to use a particular approximation. Okay, that's important. That's engineering. But to say that quantum physics or magnetism doesn't affect something like this because it's big and the quantum effects are all adding up into a predictable, probabilistic shape, that's just not true. Of course, quantum mechanics and every molecule in this applies, and it applies when they all add up. Now, if you want to say, oh, but quantum effects, there's a fundamental nature of quantum effects that when you add them up to the macroscope, they always cancel out, then great. But you know that's not true. It's quite easy to magnify quantum effects, just like it is to magnify magnetism. And the only reason it doesn't affect the macroscope more the macroscope more is because of the law of averages and the random distributions. Cheers.